Okay, so we might as well start it. So everybody can hear me okay? Okay. So my name is Chiueh. I'm a faculty member at the Computer Science Department at Stony Brook University. So this is going to be what I call fairly academic talk. So let's see how it goes. So basically what I'm trying to do today is to describe a comprehensive host-based intrusion detection and prevention system called PAID. And along the way, I'm going to talk about some of the problems that we are trying to solve in design and implementing this particular system. So we all know that a majority of the computer attacks actually exploit sort of software flaws in these network applications. So the most classical example is buffer overflow vulnerability, which allows attackers to actually modify sensitive data structures in these programs. And it's also the most dangerous type of attack because it is used commonly as a building block for modern worm attacks. And then there are other examples of computer attacks that actually exploit software flaws like syntax loopholes, SQL injection, and race condition, and so on. And then there are other attacks that have nothing to do with software flaws like social engineering, password cracking, denial of service, and so on. What I'm going to focus on today is what we call control hijacking attacks, of which buffer overflow attack is a classical example. So in this type of attacks, attackers actually try to hijack the control of the network applications by modifying some control-sensitive data structures, such as return address, function pointer, or some import function table, like global offset table, and so on. These kind of attacks actually follow a very stylish three-step recipe. And this recipe is not unlike how a hijacker actually hijacks a real airplane. So for example, the attacker would actually try to insert something bad into the victim application, either malicious code or some modification of the control-sensitive data structure. So this is like a hijacker try to sneak in a weapon into the airplane. And then the attacker would actually try to trick the attack application to transfer control to the injected stuff by modifying the control-sensitive data structure. So this is like the hijacker trying to take over the plane, the control of the plane. And then eventually, once it's in, the attacker is in, it will try to damage the underlying system by issuing some sort of system calls or do something bad to the underlying system. So it's like taking an airplane and hit some target of their choice. So given that this is sort of the standard recipe, this does not refer to any specific attack. This is a general pattern that this type of attack tend to exhibit. So we are trying to develop strategies to stop this kind of attacks so that we can have a sort of multi-layer defense to prevent this kind of attacks from happening in practice. So an example would be of control hijacking attack would be Stack Overflow. So I'm not going to repeat this. This is basically a very simple example to show that the attackers can overflow a local array and then modify some control-sensitive data structure, in this case return address, and along the way he would actually insert some malicious code, in this case some kind of in-80 instruction, which allows you to make a system call. So this is an example of how do you actually insert something into the victim application's address space and tweak the application to transfer control to the code that you injected and then do something bad by making system call of your choice. Right? So we have been trying to address this control hijacking attack problem using a multi-pronged approach. And this umbrella project is called Palladium, which has nothing to do with Microsoft's next generation secure computing-based project. It has nothing to do, it just happens to have the same name. So it actually provides multiple lines of defense against this type of attack. The first line of defense is array bound checking. So basically, a lot of this problem is because the attacker happens to be able to modify some of the data structure in the victim's application. So the right thing to do should have been that we should not allow them to do that. And most of these kind of things happens through buffer overflow. So if we can actually check the bound of every array and every buffer, then it would be a good idea to provide the first line of defense so that they would not be able to do it. And the second line of defense is that we can double check the integrity of control-sensitive data structure. As I say, this includes something like return address, function pointer, or some sort of global offset table. And the third line of defense is with this attacker is really good, that even with this kind of defenses, he can still get in and then actually try to do some damage to the underlying system by issuing some system calls. The third line of defense of Palladium is to do system call policy check. Basically, we make sure that we understand what each application is allowed to do and check its runtime behavior against the statically derived model and make sure there's no deviation between the two. So that's the third line of defense. When all this fails, there are stupid people that would screw up, that we have to do something. So our position is that there's no such thing as perfect security. You have to prepare for the situation in which your system actually get compromised. So the very last line of defense of Palladium is to provide a so-called repairable file service that basically tries to turn a compromise into a temporary outage. What we are trying to do is to develop mechanisms so that we can quickly repair a compromised system and put it back to normal order, so that we can maximize the overall system availability. So essentially, we just want to think of an intrusion just like a glitch, most just like the server overload, for example, something along those lines. So what I'm going to do today is to briefly describe the first, second, and the fourth element of Palladium, and then focus the rest of this talk on how Palladium performs the system call policy check. That's really the focus of this talk. But I want to mention the other three components a little bit as well. So the idea of array-bound check-in is not new. Everybody knows that you should do array-bound check-in if you can afford it, right? So the idea is that if you make sure that every access to an array, not only static array, but also dynamically allocated buffer, like through malloc, that you actually try to check that every reference does not exceed its associated objects bound, then that would be the cleanest solution, right? If your every program actually goes through such a process, it's actually nice, right? So that's essentially what Java gives you, right? Unfortunately, we don't necessarily have that for C, but that's basically where the problem is. Now, the fundamental two problems that you have to solve when you want to implement an array-bound check-in compiler is that for a given memory reference, you have to know what is its associated reference object. What's the object? I have a memory reference. Does it belong to this array or that buffer, right? You have to find out which object it is associated with. And then you have to check whether this particular memory reference exceeds its associated object bound, right? So usually it's the second part that's the problem. The second step, that's the problem. Now, there are commercial array-bound check-in compilers that can do something like this. And the problem with this array-bound check-in compiler is that it incurs a significant performance overhead. Typically, it's between 3 to 30 times slowdown. Okay, so let me repeat again. The idea of array-bound check-in is not new. The problem is that how do we do it fast? Okay, and that's where the innovation of Palladium comes in. So the idea of Palladium is that it's going to exploit segmentation hardware to do array-bound check-in for free. Now, just a simple sort of overview of what x86 virtual memory hardware do for a given memory reference. A virtual address in x86 architecture consists of a segment selector plus offset, right? And then at the runtime, the offset is added to the selected segment space address to form a so-called linear address, which is then translated into a physical address through the standard paging mechanism. So it actually provides a segmentation and paging mechanism at the hardware level. And at the segmentation level, it actually checks that the linear address doesn't exceed the range of the corresponding segment. Now, most of the operating systems today do not really exploit segmentation hardware at all. They just leave it alone, they use flat address space. So now, but if you look at this particular picture, like if we can somehow twist this segment limit check to perform array-bound check-in, we can actually get it for free because the hardware is already doing it. You don't really need additional hardware. The hardware is already performing some sort of check similar to array-bound check. So for example, if we can allocate a segment for every static array, even local array or global array, or for every dynamically allocated buffer, and then we can sort of organize the reference to these objects, to this static array or dynamic buffers in such a way that we can leverage the segment limit hardware check to do array-bound check-in. Wouldn't that be nice? And that's exactly what we do in Palladium. So that's the idea, that we want to exploit segment limit check hardware to perform array-bound check-in. And each array and buffer will be treated as a separate segment and referenced accordingly. So there's this little program to show you how it is actually done. So basically what we do is that if we want to do software array-bound check, then for every memory reference BI, we actually have to insert some code to check whether the resulting memory reference exceeds the bound of B or not. But then you can actually organize the way that you generate the references for BI in such a way. In this case, in particular, we are using this GS together with offset. So we are using a separate segment for this particular array. So that when the code is actually generated, that the hardware would actually check whether the offset is within the range of this particular segment, yes. And as a result, as you can see, to the right of your slide, there's actually no additional software needed to do array bound checking, but implicitly, the hardware is doing the array bound checking for you. Now, this actually gives you astonishing performance improvement. So the standard array bound checking compiler that we have is BCC. So these are the set of programs that we compile, and then we also compile a big program like Apache and so on, and the performance difference is similar. So for BCC, what we reported to the right, the third column is the performance overhead. Like it used to take 100%, and the for example, SVD pack, it gives you 120% performance overhead. That means it's 2.2 times slower, right? That's what we mean. And in the case of cache, which is our approach, it only incurs 1.82% performance overhead. It's almost nothing. It's sort of buried in the statistical noise, right? So that's the interesting results of this particular work. And if you remember, the second element of this Palladium project is to double check the integrity of control-sensitive data structure. So we apply this to protect the return address. The resulting thing is similar to stackguard, so there's nothing sort of exciting about this. But we generalize this to multiple kinds of control-sensitive data structure, and we get similar results. So the result is something like that. Again, if you add something like this kind of check, and basically the idea is very simple. Like for every control-sensitive data structure, you keep a copy somewhere. And later on, when the program tries to use it, you check whether the one that you store away and the one the program is going to use, they actually match. If they don't match, then somebody trying to screw us up, and then we can declare an intrusion, all right? And this particular check really doesn't cost you that much. So as you can see here, its performance overhead is always under 5%, right? Again, it's sort of pretty okay. In a heap where you actually protect it by 2 read-only pages so that they cannot be overflow. And then we also apply this idea. Some people complain that this is fine, but nobody's going to use it because you cannot have access to source code. So we prove them wrong by doing a version for Windows binaries as well. So we can also do this with big programs like PowerPoint and other programs in the Office suite. So that's the second component. So just to remind you, first line of defense, make sure that they cannot overflow. Second line of defense, make sure even if they can overflow, they cannot touch my control-sensitive data structure because I will double check. And the fourth line of defense is if they can actually get in and then do some damage, then I want to quickly recover the system back to an order that can actually perform useful function. So this is what we call repairable file service. And then this is actually somewhat orthogonal to this control hijacking attack. There's a general context in which this research was initiated. And that's the recognition that there's no such thing as unbreakable computer system, right? So you have insider job, you have social engineering. There's nothing we can do at the technical level. But if you try to understand then what is the loss of a computer breach, like when I say that billions of dollars is lost due to computer breaches, what exactly does it mean? So it turns out that most of them is actually due to sort of loss of intellectual property right and loss of productivity. Like, the computer is brought down or compromised, somebody has to come in, try to fix it, and at that time it's unavailable, this and that. So that's where the money is lost due to computer breach. So what we are trying to do is to recognize that a security breach is just like a failure in a fault-tolerant computing world. And they already recognize that up to a certain point, there's no point of trying to build a system that never fails. A system never fails means the mean time to fail is infinite, right? That's what you do. You make sure that it never fails. Instead, what you really care about is availability, right? And availability is like it stays up, with close to 100% of the time. So if you think about it, availability is actually defined as mean time to failure over mean time to failure plus mean time to repair, right? And what you want is availability approaching 1. That's really the goal for an individual customer. I just want my service and system to be up so that people can do useful work or customer can come in, order something. right? Now, in order to maximize the availability, you can do two things, one of two things. One is to make MTTF, mean time to failure, to infinity. Or you can shrink mean time to repair, MTTR, to 0, right? Either way can get you the same result, that availability would approach 1, right? So if we take this and then put it in the context of security, what does it mean? Like, people try to build a perfectly secure system, which means that there's no breach. Mean time between breach is infinity, right? And that's certainly a worthy goal. But the other way to think about it is maybe we can try to repair a compromised system as quickly as possible. That's not too bad, right? After all, what we really want is availability, right? And that's what that's the context in which this project is started. So given that this is what we are trying to do, then we have to ask ourselves, what do we mean by repairing a system? What exactly do people do when they say they are repairing a system after a compromise? What they are actually trying to do is to clean up, right? And clean up means that they have to first understand what damages have been caused by the attacker or the intrusion, right? So they have to establish what we call sort of damage perimeter of the system so that they can clean up, right? So the fundamental problem really is about what is that damage perimeter or associated with a particular attack or intrusion, right? So that's actually where the problem is. So we apply this line of thought to protect, in particular, an NFS server. So basically what we are trying to do is to put in a sort of a transparent proxy, if you will, or monitor device, if you will, that there's a system that can actually, a device that can actually relay NFS request and response, and then along the way you would actually log all the updates to the NFS server. And when the NFS server is shown to be sort of compromised, then we try to quickly come in and do something so that we can repair the compromised NFS server. So that's what this, what we call RFS is trying to do. Now, as I say, that there are two things that you need to do to build a repairable file service. And the goal of repairable file service is that it has to be designed in such a way that it's largely, not completely, but largely independent of the underlying network file access protocol. Like, it should be independent of NFS version 2, version 3, or it should be independent of whether it's CIFS and other network file access protocols. But regardless of the underlying sort of network file access protocol, there are two fundamental things that you need to do. First, you have to keep every update undoable, right? If you want to clean up, you have to be able to undo the damage, right? So every file update has to be undoable. For those of you who are familiar with things like network appliance, they provide something called snapshot. They give you 32 snapshots per day. That means that every 24 hours divided by 32. That's the window in which that every update, all the updates within that window will get lumped into one snapshot. But what we are interested in is that every update, every file update, I should be able to preserve its before image so that later on, if I want to roll back that update, I can. That's what I mean by every file update has to be undoable. And the second thing is that you have to be able to track the inter-process dependency. For later on, if you actually get hacked, you can selectively undo those that are left by the attackers. Okay? So these are the fundamental two things that you need to do. And then there are sort of more detailed things which I'm not going to go into. It is to do so-called contamination analysis when you actually detect an intrusion and try to come back and fix it. So we have a prototype working for, this is a pretty old system, Red Hat 7.1, and it works for NFS version 2 and 3. So there's one interesting aspect of this RFS prototype is that later on, if you decide that whatever undo operation you do to fix the damage left by an intruder, you can undo those undo operations if you want to, all right? Because, still undo operations are just updates, and every update is undoable, all right? So the good thing to know is that the performance overhead of this particular system is relatively low. Like we have to do some kind of client-side login, and we have to do something at the NFS side, servers login, and the login overhead in general is pretty low. It's under 6%, and additional latency introduced by this RFS interceptor is between 0.2 to 1.5 millisecond. And the good thing is that when the NFS workloads, the write ratio is between 30%. There's no throughput difference between NFS and NFS RFS. So NFS is pure NFS. There's nothing There's no protection at all, it's just sitting there. NFS RFS is the one that I inserted. I inserted additional things so that I can log all the updates and analyze the, tracking all the inter-process dependencies. And on the storage requirement front, it's also pretty okay. That, even though it sounds like being able to log every update seems to be very expensive, it turns out it's okay. I mean, especially when you can actually buy, 250 gigabyte for $200 today. This is really nothing. That this is a small price to pay, all right, compared to the kind of damage you would leave if you don't have any protection at all. All right. So in the end, what we end up happening is that when an intrusion happens, and all the IFS would automatically detect who is the first intruder process, and then going through that inter-process dependency tracking mechanism, you find out all the processes that depend on the updates of the first intrusion process directly or indirectly, and all these so-called contaminated processes update will get selectively undone. And therefore, you don't actually have to do anything. So that's what we mean by being able to fix or quickly repair a compromised system. Right? Okay, so now we can go back to the real meat of this talk, which is the third element of Palladium. So let me recap it again. First element, try to stop people from overflowing data structures in the network application. Second step, try to make sure that the control-sensitive data structure in the network applications are well protected because we double-check their integrity. The third line of defense is that, for whatever reason you don't like cache, array bound checking compiler, and you don't have access to source code, or you don't want to recompile your applications, then the position we are taking is that, we want to allow people to compromise or to take control of your network application. But we are saying that if they cannot issue arbitrary system call, it's probably not too bad, right? So, of course, there is already some assumption about this, that, availability might suffer. This is probably not a good solution to solve the availability problem, right? People can come in, compromise your network application, and insert the idle loop and do nothing. So that would be an availability attack. So that's not good. But we are talking about like damages that are in the form of either, compromise the underlying data files or resend an email message using the context in your address book, that kind of thing. That's the kind of attacks that we are talking about. So the idea of monitoring the behavior of an application when it runs and check this runtime behavior against some kind of static model is not new. Again, that's almost like every host-based intrusion detection system, including so-called behavior blocking products today. That's what they do. There's nothing special about this. The only problem is of this kind of system is that where do you come up with the policy, the model, right? You have to have a good model about this application, and hopefully you have one model for each and every network application out there. That would be nice, right? As opposed to right now, they have to somehow guess to get this model, and then at the runtime, check the runtime behavior against this model. And because these models are not precise, that's why you get false positive, right? And that's the general problem of this kind of approach, host-based intrusion detection system that are based on system call monitoring, all right? And this is the problem that we are trying to solve. So we are not inventing host-based intrusion detection system using system call monitoring. That's like what everybody is doing. We are trying to solve the problem of how do you come up with a system call policy for any arbitrary application automatically and accurately, okay? That's what we are trying to do. So what are people doing nowadays in order to come up with a system call policy or model for a network application? You can, ask somebody else to go through the code. I mean, this is pretty painful if you only have access to the binary. So you can do manual specification, like for a particular application. And in some sense, that's exactly where the business value is for a lot of this company, right? They actually sell you not the software that detect the intrusion, but the policies, because the policies are the most sort of valuable part of the whole deal. But manual specification is error-prone, labor-intensive, non-scalable, and so on. Or people try to do machine learning. Let's run the program, a couple of times and try to learn its system call behavior. So it's a normal mode. But of course, this, again, is error-prone, and then you need training efforts, and you sometimes will miss something because you don't exercise all the execution paths of the program. So our approach is to say that why bother? I mean, the information is always there. in the program. I mean, if you can use a compiler to extract these sites and ordering information of the system call from the source code of any network application, then you can actually get that information there. It's all there in the program, right? So there's no need to treat them as a black box and then try to do something. So we want to claim that our system, PAID, is the only host-based intrusion detection system that can guarantee zero false positive and very close to zero false negatives. Now, being able to guarantee zero false positive is nothing if you also provide a very high false negative, right? If you don't do anything, that's zero false positive, right? So the big deal is that it has to be zero false positive and very close to zero false negatives. I will show you that where the vulnerabilities of our current system is later on. So the good thing is that we have a compiler that can automatically and accurately extract system call policy from any given network application. That's a take-home point. That's the thing that we can do, right? And for now, we can only do it when we have access to the source code, but we are working on a binary version as well, right? For now, it's only for source code. So the overall architecture is that at the compile time, I'm going to extract some system call policy from the source code of the network application, and then at the runtime, I'm going to check the runtime system call pattern against this statically derived system call policy. And if there's any deviation, then we can comfortably say that's definitely an intrusion, okay? And again, this is only useful for control hijacking attacks, right? This is not going to work for, arbitrary kind of attacks. So this is not a panacea for, all security problems, obviously. Okay, so I'm going to do this first and then come back to mimicry attack. So how do we actually do it? I'm just trying to give you an outline of exactly how we do it. So we are given the source code of an application, and then we can build we can analyze the codes to get a function call graph, and then we can get a per function control flow graph. And this is a reduced control flow graph because if a function doesn't contain any system calls directly, or it doesn't call any function that eventually will call a system call, we don't care. Those functions we don't care because eventually we just want to extract a system call control flow graph, if you will, right? We are not interested in the complete control flow graph. That's for like standard compiler people. Here we are only interested in the part of the control flow graph that actually has something to do with system call. And then for each system call, we are going to extract its memory location and derive the following system call set. So we want to make sure that we understand that for each system call instance, like a system call can be made in multiple places. But for each system call site, we give it a unique label. So if your open call get called in multiple places, they would actually have multiple system call instances, and each of them has a unique memory location, right? And the way to do it is we inline the system call. So the reason we want to do it is we want to distinguish between not only the ordering in which the system call should be made, but also the places at which they can be made, right? So we want to check not only the order in which a system call should happen in a program, but also the instruction address at which those system calls can happen, right? So that's what we do at the runtime. We actually check both the ordering and the sites at which the system calls are made. But there's something wrong with this idea. The idea of extracting this system call policy or model through a compiler. That idea has some flaw because it is assuming that at compile time, you can actually get the control flow graph, right? Which is not necessarily the case. The control flow graph basically says that at the runtime program, we come here, go there. But what if you have something like indirect call through function pointer? Right? You have a function call. The target of that function call is a pointer whose value is not available at compile time. You don't even know the value of the function call. What do you mean you are going to build a complete control flow graph? Right? That's the problem. So we have to somehow deal with what we call dynamic branch target. Right? You cannot even get the control flow graph, then forget about trying to check the dynamic system call pattern against some static control flow graph. So the way we do it is that we are going to insert a special system call into the program, into the source code of the program. So the idea is that, yes, at the compile time, I don't know the value of the target of this kind of indirect function call, but I know that I don't know. That's good enough, right? If I know that I don't know, at least I can insert something, a notify system call to notify the runtime checker to tell me that, hey, this particular indirect calls whose target is actually this at the runtime. So this notify system call is to tell the runtime checker that I know that at compile time you don't know, but now I'm giving you. That's the actual value of the target address of this indirect call now, right? So that's how we solve this problem. We actually have to add additional code to the program so that we can inform the runtime checker about the values of these indirect function calls or system calls. So runtime checker is this one. Let me give you, so this legitimate check is what I mean by runtime checker, right? Okay, so this solves the problems of dynamic branch targets. The kind of branch instructions whose target address is not available at compile time. That's what I mean. But then there are other issues as well. No, programs are actually more complicated than that. It's not just about dynamic branch targets. There are things what we call asynchronous control transfer, right? Like this such things as a set jump and long jump, right? Out of the blue, you set jump somewhere, and then you want to do a long jump. So there's a sort of unconventional control transfer, if you will. So we have to deal with this issue as well. Our system can deal with that. Like we can actually keep track of the current cursor of this system call control flow graph at the time of set jump. And when you do a long jump, I sort of put the cursor back to the place that we recorded. So we can resynchronize the runtime behavior of the application with the system call graph that we are checking with, right? And then there's the signal handler, right? Signal handler has the characteristics is that at the compile time, you cannot find any call instruction that actually call a signal handler, right? By construction, nobody is calling signal handler. The only guy that's calling signal handler is the kernel. Right? So if you just analyze the source code of the application, of course you cannot see any instruction that try to call a signal handler, right? And that we can also handle. So this is actually similar to this indirect function calls. And then there are things like, at the compile time, you don't even see the code because this actually get loaded at the runtime, like you do a load module. You don't even see the code. How are you going to analyze it, right? So we can also deal with dynamically linked library as well. So this is not DLL, just DLL. This is like a DLL module kind of thing. You actually load the module at the runtime. So our system can deal with this kind of peculiarities, programming primitives as well. So let me go back to mimicry attack. So given that we can derive a system call policy or model at the compile time, and we can deal with dynamic branch targets and asynchronous control transfer and so on. These are all fine, looks okay. The only problem is that the bad guys still can get you, right? And this is a so-called mimicry attack. So the way that bad guy is going to behave is like this, that the guy is going to come in, right, exploit the buffer overflow vulnerability and comes in. And he understands that the system call model of this particular victim application, maybe just by leveraging our tool, right? He can compile an application using exactly our tool to get the system call model. And then he's going to follow the system call model specified in that in the policy and pretend to the runtime checker as if everything is okay. And if one of the system call in the application can actually do the damage, then he can eventually hit the application with the system call, right? So for example, application actually just makes 3 system call, right? Open something and then eventually do some exec, all right? So when he comes in and then takes control of the application, he will follow all the innocent or non-harmful system calls until the program control flows go to the sensitive system call exec. And then at that time, he can hit the application to do something that he wants. All right. So this is what's referred to as mimicry attack, because the attacker actually tries to mimic the legitimate system call sequence in the system call policy or model. Right. So there's no violation. Right. From under the kernel, I'm seeing all the runtime system call pattern. Everything is okay, because the attacker actually does exactly what the system call policy is saying that the application should behave, right? So there's actually no deviation. But as long as there's some sensitive system call that the attacker can use, then the attacker can hit the application or the underlying system. So none of the existing commercial or research host-based intrusion detection system can deal with mimicry attacks. Like, they can come in, and if they are really good, they can actually do exactly this, right? So then how do we deal with this problem? So if we think about it, in order to mount a mimicry attack, what do you really need to do, right, as an attacker? The first thing you need to do is, of course, you have to you have to come in and compromise the application, right, by taking advantage of some buffer overflow vulnerability. And then you have to issue all this intermediate system call without being detected, right, because you are trying to emulating the legitimate system call sequence in the policy. But this is in general not too bad. Like, people can actually do that. Almost all the system call can be turned into no-op by specifying the proper arguments. And then in the end, when you reach the system call that you need, you can actually hit the system by issuing the system call with whatever argument that you like, so that you can achieve your purpose of mounting an attack to the underlying system. But along the way, in order to be able to issue this each intermediate system call appropriately to fool the runtime checker, you have to be able to grab the control back, right? So what happens? I have an application, I grab the control of the program, right? And then I try to issue system call. But every time I issue a system, I have to get the control back so that I can issue the next one, right? So that's the thing that the mimicry attacker has to do, that he or she has to be able to get the control back. And it's actually not too bad, not too difficult to be able to do that, because once you are in, you can manipulate the stack information any way you want it, right? As if it's actually coming back. There's actually a legitimate function call eventually leads to any particular system call. So it's actually not too bad. That you can actually set up a stack so that eventually you get the control back. So given the recognition of how a mimicry attacker is going to work, then we can actually use the following countermeasures against the mimicry attackers. So basically what we are going to do is that we need to check system call argument. Remember, as a last system call that the mimicry attacker is trying to use, he actually tried to use some different system call argument. So for example, that's the exact. So maybe he tries to do a bin share, for example. So if we can somehow check the system call argument of every system call, in other words, the system call policy or model includes not only the order and site of the system calls, but also the arguments that they are allowed to use, then it would tighten up the window of vulnerability that attackers can exploit. So even though the attacker can emulate the exact sequence of system call, if in the end he cannot specify arbitrary system call argument, that's still not too bad, right? So that's one way to counter these mimicry attackers. The second thing you can do is that you can make sure that the mimicry attacker cannot get the control back. So think about it, how does the mimicry attacker get the control back? Presumably, he actually inserts some piece of code to the stack or somewhere, or in the heap somewhere. And then every time he makes a system call, then you set up a stack such that when the system call is done, the control comes back to its place. So that means that the return address must go back to the place where he inserted the code, right? So this is either in the stack or in a heap, most likely. So if we can actually check every system call, when it's done, whether the return address of this system call actually go to the stack or go to the heap, then we know this looks suspicious, right? Usually it's from the code segment. How come the return address is actually going back to the stack or going back to the heap? And the third countermeasure that we should do is to minimize the ambiguities in the system call model. Now, there's a little bit digression here, that the kind of system call model that PAID can construct is, in technical terms, non-deterministic finite state machine. It's not a deterministic one. That means that there are still some ambiguities in the system call control flow graph. So in this example, for example, in this, if a program contains this if then else, so if A is greater than 1, then do open. Else it does open and write, for example. Now, so as you can see that at runtime, if I see a open, I don't really know which arm of this conditional branch instruction the program is taking. When I see open, right? I may be able to see when I see write. When I see write, maybe I can tell that is actually the else arm, not the then arm of this conditional branch, right? And then there are some other cases in which that make the system call control flow graphs sort of ambiguous. So for example, if you have a function that get called from multiple places, and that function actually makes a system call, then when you see that system call, you don't really know from which call site that this particular function is invoked, and so on. So when you return, you don't know which one to go. So I can give you an example why this is a problem. So in this particular case, I have two functions in this program, main and foo, right? So actually, this is not the example I want. Yeah, this is the example I want. So main and foo in this case. So the main function actually makes two calls to the function foo, and foo in itself actually makes two more system calls, system foo, and these system calls are identical, right? So you can see that if I follow the usual thing, I can take the red. When I make the first foo function call, I go to the foo function and then come back. So after that, the next legitimate system call is actually sysfoo, right? So if I take this, hopefully this is not a problem. So if I go this and then come back here, then the next one I want to call is another call to the foo function. So the first system call in foo function is sysfoo. So that's one possibility. Now, if I'm making the second call to the foo function call, then the next system call should be exit, right? So there's actually a way to distinguish between these two foo function calls. But there's some ambiguity there. What if I can say that I can go here, and then when I come back, I actually takes the blue one back. So my call path is actually going to the foo function through the red one, and when I come back through the blue one, all right? Because this is the only graph that I get. So the graph never actually specifies that there's a red pair and there's a blue pair. You just specify that you have these edges, right? So at the wrong time, when I'm checking the system call pattern against this graph, I don't know there's actually a red pair and there's the blue pair. So all the possibility is allowed. So after the last instruction of foo, I can actually go back to this return foo, or can go back to another return foo, right? And that's where the ambiguities come in. And that's why I say that the system call control flow graph that the pay construct is ambiguous, right? So this is one possibility that attackers would actually try to use. That attacker would actually try to exploit this ambiguity so that it can sneak in some system call pattern that is not allowed in the original program. But because when Pay built its system call control graph, there's some ambiguity that it actually allows it at the wrong time. And the technical term for this kind of system call pattern is called impossible path. The impossible path in the original program, but because the way that we build our system call control flow graph, we actually allow it at the wrong time. Okay, so we actually have to tighten that loophole as well. So the technical problem is really about how do we convert an NFA into a DFA. So without boring you with all the details, what we basically do is the following two things. We use the graph inlining to disambiguate the return address for function with multiple call sites. And every recursive call chain is inline and turned into a self-recursive call. And then another step that we need to do is we do system call stop inlining so that we can disambiguate the two system calls that are identical and that are two arms of a conditional branch. So in that particular example, what I'm showing you is that if I have a conditional branch and in both arms I make the open call. Now if I can inline this open call, then I know which one we are talking about, because by looking at the address of this open call, I know that which one is the one that the program actually takes. So that's where system call stop inlining can help you. But this is a relatively expensive operation, because as you can imagine that every system call instance now, I have to inline it so that I can disambiguate the potential ambiguities there, right? So, okay, I'm going to skip this. So, in the end, what exactly does PAID provide? Like, given all this sort of theoretical stuff about what we should worry about when we build a PAID-like system, what kind of checks that the PAID actually provides? It actually checks the ordering of the system call. Okay, open, exec, and then do some set attribute, this and that. And he also checked the site of every system call. So even though a program makes multiple calls to the same system call, we can distinguish them. Okay, this is part of this system call stub inlining. And then we try to defeat the mimicry attack. If you remember, mimicry attackers actually try to mimic the legitimate sequence of the system call. And this legitimate system call sequence is derived from the program, just like what we do. Right, so they apply our tool to derive the legitimate sequence and then use it to emulate the legitimate system call sequence until the system calls of interest to them. So in order to defeat this, what we are trying to do is that we actually insert this random notify system call at the load time. So when I start the program, I actually randomly insert some system call, which is not in the original source code. So that means that at the runtime, my legitimate system call policy is actually different from one instance to the next. So I start Apache, this time my system call policy is slightly different because I'm randomly inserting this notify, all right? So that's what we do. And then we also check stack return address check. That's what I just talked about. Like every time I have a system call go into the kernel, before I return, I check whether the return address go to the code segment or not. This is to prevent the mimicry attackers from grabbing the control back whenever they fake a system call. And all this checking is performed in the kernel and so on. So in the end, it's actually sort of relatively efficient. So let me give you some examples of why performing all these checks are necessary. If you just check the ordering, like you do set UID, read, open, statistics, and write, then the attackers can just emulate this sequence, right, without checking the site. So it's very easy to defeat this kind of system call ordering check only. So the guy can actually just do that. Once he hijacks the control of the application, he just issue that these system calls according to the order as derived from the system call policy. Now, if you do ordering and site check, then the attacker would actually, and again, it gets the control. Then he has to actually issue the set UID and then issue this in place, so that all these system calls have to made in the same place as this system calls happens in the original program, because we are checking not only the order but also the site. So the attacker, if the attacker really wants to issue this system call, he has to make sure the system call is made at the place that they are supposed to be. And that means that the attacker has to be able to grab the control back. And in order to do that, they have to set up stack. So that makes his job slightly more difficult. So that's what the site check gives you. Now, if you can do ordering, site, and stack check, that means that we want to prevent attackers from grab the control back. Then you can do something like this, and then send it to do set UID, and then the control would actually come back to the original flow. The control would not go back to the attacker, because we are doing stack check. The return address has to go to the segment, code segment, as opposed to go to the stack or heap. Now, there's still some problem even with stack check. If the guy really doesn't need to make a couple of system calls, for example, if the guy comes in and compromises a program, and then the next system call is exactly what he needs to damage the underlying system, then he doesn't need to grab the control back. And that's the only weakness in this case. So the same deal, I get the control, and I can make a system call to exec, and even though the control doesn't come back to the attacker, it's okay, because he doesn't care. He just needs one shot, and if it's good enough, then that's good enough, right? So I'm saying that even with ordering, site, and stack check, there's still some window of vulnerability that attacker can try to do. That's what I'm saying. And in order to do this, we can further do this random insertion of notify call, right? The mimicry attackers try to be a good citizen by emulating the legitimate system call sequence. But if at the load time, I actually get to change the system call policy slightly, then he's not able to guess necessarily. And that's what this random insertion of notify system call is trying to do. So buffer overflow tried to do something, and he actually forget about this particular notify call, because this one is what I inserted at the wrong time. So at the wrong time, when I check that, how come this guy is actually skipping a notify call? Then we know this is not our guy, and that's how we detect these mimicry attackers. Okay, so I'm going to skip this one. The last item I want to talk a little bit about is the system call argument check. Basically, what we are trying to do is to check the system call argument. As I say, that at the end of the day, you really want to check the system call argument, as well as the ordering, the site, and stack. So basically what we do is very simple. We go through the same program and derive using data flow analysis and classify the system call arguments into 3 categories. Either things that you can determine statically, static constant, or things that you cannot determine statically, but you know their value remain the same. Things like you get it from environment variable, you get it from configuration file, those things. The values of the system call arguments never change during the lifetime of the program, but you cannot figure them out statically because you can only run them and only then you know. So this is so-called dynamic constant. And then everything else, dynamic variable. So we actually go through such a process, and it turns out that more than 50% of the system call arguments belong to either static constant or dynamic constant. You can actually figure out their value once the program is initialized. But still a substantial percentage of them are dynamic variables. So what can we do with dynamic variables? The only thing we can think of is that we can maybe derive some partial constraint. Like in Apache, you will say that this is my root directory, and every time user gives you some URL request, that you concatenate the two, and that forms the object, right? So we can say that that particular object name is a system call argument, and at least we know there is some partial constraints of that system call argument. Or you can try to insert a notify system call, so to enforce the application to go through some system call argument computation process. All right, and that's another approach that we are taking. So as I say, at the end of the day, our system has very close to 0 false negatives. So what is the window of vulnerability for our system? The one possibility is that the guy comes in, compromise the application, and the next system call in the legitimate system call policy is exactly what he needs. And the system call argument of that system call is a dynamic variable. That's why we cannot check. Under the condition, he can attack the application. That's one way. The other way is sort of the more subtle one, that the guy comes in, compromise the application, instead of mounting, sort of inserting the malicious code, he just performs some kind of arguments modification, so that the system call argument would actually modify in a way that he likes. Then that's also something that we cannot do. In both cases, these kind of attacks are very rare, that we cannot find anything like that in the field at this point. So we have a prototype implementation, just give you a throughput overhead. So basically, we compile a program, right, and derive its static, its system call policy and model, and at the runtime, we will check the runtime system call pattern with this policy, and then we will try to check both the ordering, the site, and stack, versus we will add some random notify. So these 4 columns give you like the generic paid, and this give you doing paid plus stack address check to make sure that the attacker cannot get the control back. And the 3rd column is with a random insertion of notify, and the 4th column is everything. All right. So as you can see, that still this is not too bad. The performance overhead is okay, but this is really nothing nothing that exciting. That's almost what everybody is getting. If you do host-based intrusion detection, you will get something like this. The big deal of our system is that we can derive the system call policy automatically and accurate. Right? So conclusion, Pay is perhaps, arguably, the most efficient and comprehensive and accurate host-based intrusion detection and prevention system. It can automatically generate per application system call policy, and system call policy is in the form of deterministic finite state machine, so that we can eliminate the potential ambiguities to eliminate so-called impossible paths. And it also performs one of the first sort of extensive system call argument check, and it can handle function pointer, asynchronous transfer control, and guarantees no false positive. Because if there's a deviation, there is an attack. It's just that it has a very small window of vulnerability that attacker can sneak through. So it has very close to 0 false negative. It's not 0. And it can block most of the mimicry attacks. So what we are trying to do is mainly to derive a binary paid versions for Windows platform. And we want to further reduce the latency and throughput overhead. And most of all, we want to perform a better job at analyzing the system call arguments, so that we can cover most of the so-called dynamic variable category of system call arguments. So if you want more information, you can go to this particular website. We also have a prototype system, so if you guys are interested in trying, we'll be happy to send you a copy. Right, so if you have any questions, I'll be happy to entertain them. Yes, so the only thing attacker can get is our tool. So he can figure out that statically what our tool would try to do. So the only thing we can do there is to do this load time sort of notify system call insertion. So load time means that when you start a program, I'm going to insert some random system call to twist the system call policy a little bit. And this is random. So even though the attacker has a complete source code of our tool, he's not able to figure this part out. Okay, so thank you.